Okay, guys, today we're going to talk about electron configuration. I'm going to go through a bunch of things with you. Let me bring up the screen and let you see what we're going to do here. Sorry, I'm not in class today. I've got some things I had to do, but I'll be back on Monday. No worries. Let's see. I need to share my screen. There we go. Okay. Almost there. So, first thing I need you to do to make sure you did was pick up a blank periodic table as you walked in the door. We're actually going to color that here in a little bit, and today will be kind of an easy day a little bit. Electron configuration is something that'll make sense to you. So if you got out your notes, the blank periodic table, and I'm going to go over your homework problems with you real quickly. There are a couple in there that may not have been fair to ask you, but you know, if you're doing your reading, you probably know what you're doing. So there's the homework questions. The first one said, how do two sublevels of the same principal energy level differ from each other? This is some vocabulary that we haven't really had in our notes or that I've said out loud, but the energy level is the same as the period generally of the periodic table. These sublevels are the SP, D, or Fs. So let me change my color here. So the sublevels here are going to be like your shapes, your SP, your D, and your Fs. So the sublevels include different shapes of orbitals is what they were looking for. So if you had S orbitals, they'd be spherical, Ps would be peanut shaped, and et cetera. Question 5 says the energies of electrons are said to be quantized. You can't split electrons. It's a lot like our penny question on the lab. So pennies can be quantized, as can electrons. So, and in order for an electron to move from one energy level to another, it has to absorb a certain amount of energy. It doesn't leave any part of the energy behind. And so they can be completely moved from one energy level to another through one quanta of energy. Anyway, how many orbitals are in the following sublevel? We did a little bit of this at the end of the period yesterday, and this might be easier if you think about it in terms of electrons first. So like the 3p sublevel, if you were to go to the third row of the periodic table in the p block, there are 6 elements there representing 6 electrons. It goes from, let's see, aluminum all the way over to argon. Is that right? Yeah, aluminum over to argon. And so there would be 6 electrons there. Well, the number of orbitals you would divide by 2, so it would be 3 orbitals. With the 2s sublevel, you would have 2 electrons. If you divide that by 2, you get a single orbital. The 4p sublevel would be the same as the 3p, so it would also have 3 orbitals. And then the 3d, 5. There are 10 in the D, and so 10 electrons in the D sublevel or D orbital, and so you would have divide by 2 to find out the number of electrons, which would be 5. So there we go. On 36, it said arrange the following sublevels in order of increasing energy. So you would go from something that's close to the nucleus to something that's further from the nucleus. You can also just look at the energy levels. You have a 2, a 3, and a 4. That they would be in that order. But as far as assigning them, you would assign in the 3p before you assign in the 3d. We'll do that today with electron configurations. So the 3p is actually lower in energy than the 3d. So here, what's the maximum number of electrons? This is more what you understand. So if you went to the periodic table and looked in the S block, period 2, that's where lithium and beryllium are, there's just 2 electrons. For the 4s, it's also an S, would be 2 electrons. The 4p, p can have 6, f can have 14, p can have 6 once again, and the d's you would have 10, 2, and this last p would have 6 as well. If you divided them by 2, that would tell you how many orbitals you had for each of those. That one's pretty straightforward. Just looking at a periodic table and you can count across the block. So there we go. On 39, I made this really big so I could describe this. This you would have had to do in your reading. I know in a couple of classes I talked about what the 3 and the p mean, but I didn't talk about what that other 3 means. And we'll do this today. But I guess we can start now. A little learning right now. This is the energy level, right? And so it's the third row of the periodic table, the P block. That's what the P represents, is the shape. And in this case, or sublevel, if you like, is the peanut shape. This 3 up here represents how many electrons you actually have assigned. And we'll do this today in class. This is part of electron configuration. So in the third energy level, in P-shaped orbitals, you have 3 electrons. That's what this 3p3 means. It could be 3p1, it could be 3p4, 3p6. As long as it was from the 1 to the 6, that would be fine. Yeah, and this is kind of the same question, just written out in sentence form. So here, how many electrons are in the highest occupied energy level of these atoms? So you would go find barium. Barium is in the 6s. And so if it's in the 6s, it would have 2 electrons represented in its outermost. Its outermost is the last one you assign in, is the 6s. Aluminum is in the second energy level. It has 2 in the s and then 1 in that p. So this one would actually have 3 electrons in the outermost occupied energy level. The energy level would be the third energy level, and it would have 1, 2, 3 electrons in that energy level. Sodium is the very first one in the third energy level, so it would just have 1 electron. And then oxygen, if you count over to oxygen from where it starts in the second period, it has 6 electrons. These would be called, like the highest occupied energy level, these would be called the valence electrons. So those are valence electrons, outermost electrons, the ones that are going to be involved in bonding and dictate the behavior of the actual elements. Yeah, there we go. So what we're going to do now is we're done with the homework. You can put that away. Is we're going to color a periodic table, and you should have a blank periodic table you picked up as you came in, and you need 4 colors. You can use whatever. I wrote 4 colors of your choice in here, so you can choose 4 colors. Up on my demo desk is a box of map pencils. You can choose 4 random colors out of there, whatever you like. And you're going to color your periodic table like this periodic table I have up here is colored. So you're going to color your S block, which is, your S block. Oh, that's white. It's not going to show up. Your S block, which is over here, your D block, which is here, and your P block, which is here, and your F block, which is on the bottom. Color them different. Take a little bit of time. You can shade them, make them pretty if you want. If you brought your own colors, knock yourself out. But I'd ask that you just hit pause, go and do this color for a little bit, and then come back. So pause. Okay, so hopefully by now you have a colored periodic table. We're going to go through and use this to do our electron configurations. So keep the colored periodic table out, and let's go through a few of these together. So what the electron configuration really is kind of a description of where the electrons are arranged or where they're found around the nucleus of the atom. So you'll have things like 1s2, which represents first energy level, an S shape, and then 2 electrons, like we had in the homework that I didn't show you how to do yet. There are 3 rules that govern the filling of these atomic orbitals. And while this doesn't really go back to quantum numbers are based on these as well. So the Aufbau, and you got to know what these 3 are and the names that are associated with them. So the Aufbau principle says that electrons enter orbitals of lowest energy level first. So they're going to enter in the 1 first, and then the second energy level, and then the third, and then the fourth, and then the fifth, and so forth. There will be a few that go out of order, like we'll go to the 4s, and then we'll step down to the 3d. But they always go in the orbitals of lowest energy level first. That's Aufbau principle. The Pauli exclusion principle says that an orbital only describes 2 electrons. And so you can't have more than 2 electrons per orbital. And the last thing is important, they have to have opposite spins. So if one is in one direction, spinning on its axis in one direction, the other one is spinning in the other direction, the opposite. Hund's rule says that when electrons occupy orbital of equal energy, they're going to enter each orbital one at a time with parallel spins and then double up after that. So they're going to 1 electron enters each orbital until all orbitals contain a single electron with parallel spins, like 1, 2, 3. Then they'll go back and refill. That's why yesterday we did plus half, plus half, plus half, and then negative half, negative half, negative half. I'm going to show you that in an orbital diagram with arrows representing the electrons, which will help a little bit more explain that, help to better explain that here in a few minutes. All right, so here they are also. Here's the Aufbau principle. They fill lowest energy level first. This little graphic over here that I've circled, That's how I learned in college how to do it. I'm going to teach you a much better way to write electron configurations, but they're going to assign in the first energy level, then the second energy level, then from the second to the third, and the third to the fourth, and so forth. But it's a whole lot easier to see on the periodic table than it is by drawing this little 1, 2, 3, 4, 5 nonsense. This is what they tried to teach us as a quick way to do it in college, and it's not a quick way to do it at all. The Pauli exclusion principle, we already talked about that. You're going to have opposite spins, so there'll be one in one direction and one in the other. And the last one, Hund's rule, you're going to fill each one first, each orbital first, and then go back and refill them afterwards. So let's just go do a couple electron configurations, and then I'll show you what each of those rules are in terms of writing electron configurations or orbital diagrams. So I want to do carbon first. We're going to go through and do that. Yeah, I have them down here. Okay. So this periodic table looks a little different than yours. It has the 3 colors. Maybe they're the same, maybe not. I've moved helium over. So helium is not over here right now. I've moved it over here so it's easier for us to do these. But just remember, helium is in the S block. It's just on the other side. We've colored it. Hopefully you've colored it differently. So here, let's do carbon. Let's write an electron configuration for carbon. So what you do when you write an electron configuration is you go through each one until you get, now what we want to end up with here is carbon. So I'm going to go through my periodic table and write where these things are, energy level, sub-level, the shape, until I get to carbon, and then I'll stop. And then that'll be our electron configuration for carbon. So if I go through that first energy level, and these are numbered 1, 2, 3, 4, 5, 6, 7, of course. If I go through the first one, that would be 1. I went through the S, and I went through 2 elements, which represent 2 electrons. That would be the 1s2. Now, we don't say 1s squared. There are people that do that, and they don't know what they're talking about. It's 1s2. It's first energy level, S sublevel, spherical, and it has 2 electrons. There is nothing over here, so we're going through our 2s now, and then I write 2. Oh, that's not a 2, that's an S. 2s, and I went through 2, so I write 2. Now I'm going to keep going until I get to carbon. So I'm going to go through here to carbon. That is the second energy level still. It's now the P block, and I went through 2 of them, 2. You guys just wrote your first electron configuration. That's all there is to it. And we're going to do a bunch of them. So this would be the electron configuration for carbon. What it means is, like we built the one in class in the PowerPoint, you would have the 1s with 2 electrons, that'd be a sphere. Then you have the 2s spherical with 2 electrons. Then you would have 2 of the 2p orbitals, each with 1 electron, being a total of 2. And I'll show you the each with 1 electron in a minute, or in a little bit. That's carbon. Let's go do zinc. Zinc's longer. It'll take, it'll be a little bit more, but we'll be okay. Let's get rid of this. Let's go do zinc. So here is zinc. So I got a long way to go. So the first one, if I go through these 2, I have 1s, and I went through 2. Now, if you're writing on your periodic table, it's probably not a good idea, but you can scroll across, right? Okay, so here's 2s2. And then I'm going to go all the way through over here where we had carbon a minute ago, 2p, and that was a total of 6. And we'll go through this D, and it'll be the S, 3s2. I'm going to go all the way through the 3p, third energy level, P-shaped, and there were 6. I'm going to go all the way through these, which would be 4s2. And then I'm going to go from here all the way to zinc. And remember that the D is just a little bit closer to the nucleus, a little bit less energy. So what we're going to do 3D, and it would actually be 10. That is the electron configuration for zinc. I know it's long. And you're going, oh my gosh, what if he asks us to do something in the F block after? I will. We'll do it. I won't do it on an exam. It takes too long. But for practice, we may do a couple of those really long ones. And I may teach you a way to make them shorter. We'll see. So there you go. There's zinc. So that is your second electron configuration that you've done. Good job. So checking our work down here, there they are, 1s2, 2s2, 2p2, and 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So this periodic table here is the way the periodic table really is. I kind of drew it for you in class roughly, on the board, but it actually, this is weird, it actually assigns those 3Ds before it does the rest of the Ds. I don't know why. I did in the past, but I don't remember why, but it does. And so, like I said, exams, quiz, I'm not going to ask you to do something in the Fs. That's just cruel, but we'll do one right now, just, a long one just to see what it's like. So let's do europium down on the bottom. It's got 63 total electrons. As a matter of fact, let me point that out. Carbon has 6 total electrons. You could always check your work. Carbon is element number 6, right? So it has 6 valence electrons. You could count those things I'm circling up there at the top, 2, 4, 6, to double check and make sure you've got them all. You could do the same thing with zinc. Look, 2, 4, 10, 12, 18, 20 plus 10 is 30 electrons. So you could add them all up just to make sure you're doing it right. Totally fine. Let's go do europium. So it's down here on the bottom in the 4F, and I'm going to use this periodic table to do it just because it's better. But the 1s going all the way across to helium would be 1s2. And then I'm going to go through my 2s, 2s2. Then I'm going to go through my 2p, 2p6. Then I'm going to go through my 3s, 3s2. I'm going to run out of room. I'm going to have to use another line. Oh well. Then I'm going to go through my 3p, 3p6. Then I'm going to go through my 4s, 4s2. I will go through this 3D1 and all these others, so I can just write 3d10. And then I'm going through all these 4p's. Oh Lord, I'll run out of room. 4, I'm on the next line, 4p6. And then I'm going through 5s2. And the 4Ds all the way through all 10 of them, 4d10. And then to go through 5p, 5p6. We're getting there. So now I'm in the 6th energy level, 6s2. I am going to assign that 5d1. I know that's weird. 5d1. And then carry it over to europium, which is the 6th one of the Fs. So that would be 4, because it goes down 2, 4f6. Now you may see this written differently. So this is totally okay. This is the complete electron configuration for europium. It is written correctly, but some textbooks and professors like to order them according to energy level. And so they'll group all the 1s, 2s, 3s, 4s, 5s, 6s together, and they'll reorder this so that your 4F is actually written before your 6s2 and your 5Ds and stuff. That's okay. You can do that, and you'll see that in your homework a little bit. But if you are asked to write an electron configuration and you write it like this, it is still correct. It's not wrong that you didn't write it in order of the energy levels. College Board and AP Chem would accept both of them as well. Most freshman professors would, unless they have, an ego trip and they just want you to make sure you're doing everything like me with sig figs. Anyway, but there we go. We did a big one. Yeah, look at that craziness. And this is typed out the same way that I wrote it, finishing with the 4F6. That is not wrong. So don't you think it would be easier if we didn't have to write like the entire electron configuration? Like maybe if there was a shorthand way to write it, of course. And there is a shorthand way to write it. And I'm going to show you the shorthand way. And from this point forward, you can pretty much use shorthand notation unless it asks you to write the entire ground state electron configuration. If it does, you got to write the whole thing. But if it doesn't, you are free to write the shorthand notation. And let me show you how to do that. So with shorthand notation, we make the assumption, which is correct, by the way, that noble gases stay the same all the time. That noble gases, their electron configurations don't change, that they're filled. And so the other ones can tend to gain or lose electrons. And so it's important to write those that are after the noble gas that came before it. So let's do sodium real quick. I'm going to go back up and do it, but I'm going to go write the electron configuration for sodium. I'm going to write it off of this one here. So we're going to do sodium real fast. Sodium is number 11. It's right here on the periodic table. I've circled it. We're going to write its entire electron configuration, and then we'll go back and write the shorthand notation. So we would do 1s2. We would do 2s2. Then we would come across our p's and do 2p6. And then we'd just go to the first one here, which would be 3s1. That is the entire ground state electron configuration, and it's totally right. But if we wanted to write the shorthand for this, what we'd do is go backwards from sodium to its nearest noble gas that I went through, which is neon. And I would write in brackets neon, which represents this entire electron configuration right there. And then afterwards, I just write 3s1. That is shorthand notation. And you are more than welcome to use it now that you kind of know what you're doing. Unless it says to write the entire ground state electron configuration, you can write shorthand. But remember to go backwards to the previous noble gas, one that has an atomic number that is lower than the element that you're talking about. Don't go forward and write argon. That's wrong. What if it were neon? What if I asked you to write the electron configuration for neon? Would it really be acceptable just to write neon in brackets? Yes and no. I mean, I would prefer that you actually write like helium 2s2 2p6. But if you wrote brackets neon, it's not wrong. It's just lazy. But that's all right. We'll have that discussion later when you guys actually do that. Okay, so going back to some shorthand notations, I'm going to show you this in terms of an orbital diagram. You guys don't have to do this. You can write it on your paper if you want to, but I just kind of want to show it to you. Sodium has one additional electron beyond its noble gas. And if we did that, we would write the electron like this with an arrow. And that represents that one electron in the 3s. If I were to write its electron configuration, I would just write like I did before, neon 3s1. There you go. Magnesium, same thing. If I were assigning electrons, this orbital diagram, each one of these blanks represents an orbital. The S has one, the P's have three, of course. If I had magnesium just has two beyond it. So I would do an arrow up and an arrow down to represent those two electrons. If I wrote its electron configuration, it would just be neon. Oh, that's sloppy. Let's start that again. It would be neon 3s2. That's still sloppy. I'm having issues with my brackets. I got it. Aluminum would be neon 3s. And if you count over from the beginning of the third energy level, 1, 2, and then in the P, there would be a third one of 3s3. Don't write that down. 3s2, 3p1. There we go. Now, if I were doing the orbital diagram for this, I would do up, down, meaning I assigned in the S, and then I would come and I would assign one in the P. There you go. So that is shorthand notation. And also kind of, I've shown you a little bit of orbital diagrams. You're not going to have to draw orbital diagrams for us. They're just a helpful way to explain what's happening with the electrons in terms of assigning them to certain orbitals. So let's do silicon. Silicon would be, and I'm going to do this. I'm going to erase this stuff up here and scratch this out and say we're going to do silicon up here. So silicon has 14, right? So neon, let's do the whole silicon. That's fine. So if you're looking at a periodic table, I would go through the 1s2, and I go through the 2s2, and I go through the 2p completely 6, and I go 3s2. And then silicon is the 1, 2, 3, fourth one there, 2 in the 3, so it'd be 3p2. If I were writing the shorthand for that, it would be neon. Sure I'm doing this right. And it would be 3s2, 3p2. That would be the shorthand notation. Doesn't save you a whole lot doing shorthand notation just in the third energy level, but fourth, fifth, sixth, seventh, oh yeah, man, saves all kinds of time. If I were doing the orbital diagram to represent these 4 electrons, you would assign one here, and then you assign the next 2 in the P, 1 in each orbital before you go double them up. So this is like the plus half, and then you would do another plus half before you would go back and do negative half, negative half, negative half. I used to teach it as though there were houses on a block, on a street, and only one person gets to live in a house before you go double them up. So one person in each one of those houses on the block, and then you can have a second person go in, but a maximum of 2 is allowed. So anyway, so there we go. There. Oh, there's our silicon on the bottom. So neon 3s2, 3p2. So we're going to go do a few of these other ones just to kind of show them to you. Just for more. Actually, you know what? Well, they're already written for you. I'll just go through and show you the orbital diagrams for explanation. But here, The 4s, it says over here on the right for the configuration 4s2 3d5, that would be 4s2. And those 5 electrons, I would assign 1 in each one of these before I double up, but I ran out, I got 5. So there's 1, 2, 3, 4, 5. So that would be 4s2 3d5, right? On the next one for iron, iron's just one more over, so it's going to be 3d6. I would have these 2 in the 4s, and then I would assign 1 in each of these d's, and then I would go back and double that one up. Same thing with cobalt, boom, boom. And then I would have, you assign 1 in each one. Don't even double them up when you know they're going to be doubled. Just do 1 at a time and then go back and double them up. Did I skip something there? 3d5, 3d7, 3d7, 3d8. So here, nickel, 1, 2, 1, 2, 3, 4, 5, and I'm going to 8. Down 6, 7, and 8. That would be the orbital diagram showing where each of those electrons are represented in each orbital of the 3Ds. Copper's a little weird though. Copper does some strange stuff. So I'm going to erase this here and we're going to talk about copper real quickly. So let's get rid of this nickel and we're just going to do copper up here. And don't worry about this over here too. So I'm just going to do the orbital diagram for copper. So if I had 29, I would end up having 9 electrons in the D. So I'm going to go and do 1, 2 in the S, and then I would, oh, I should have written the electron configuration. Let me go ahead and write that. So it'll be argon 4s2 3d9. It's right before you get to zinc. So it's right before you finish the Ds. You have this 1 electron that's not there. So you have 9. So 1 and then 2, 3 and 4, 5, 6, 7, 8, 9. So that's what you think the electron configuration would be for copper. Makes sense, follows all the rules and stuff I've taught you today, but it doesn't do this. Instead, what happens is because the 3D is just slightly lower in energy than the 4S, and that's how I explain it anyway, it's actually more stable to have this electron be placed in the 3D. And so copper is one of the exceptions to this electron configuration. There are really only 2 exceptions that we're going to have you guys memorize, copper being one of them and chromium being the other, and I'll show you it as well. But with copper, we wouldn't write 4s2 3d9. We would actually write 4s1 3d10. It is more stable with that electron in the Ds rather than in the S's by itself. So yeah. Copper does this. Yeah, oops. And you just got to know it. Now, the whole column does that. So if I come down here and I look at the expected and the assigned things for copper and chromium, this is exactly what we're talking about. Look here. Here's the expected for copper based on all our rules, but it doesn't do that. Instead, it drops 1 down to be more stable and the 3D gets 10. Look what happens to chromium. Chromium, the expected, is 4s2 3d4. If I were to write the orbital diagram for this, I would have a 4s and I have my 3ds, 1 and then 1, 2, 3, 4, 5 in the Ds. I would assign my 4s2 and then I would assign the 4 that are remaining in the Ds, but it's actually more stable half filling the Ds than it is to have one of them empty. And so what'll happen is it doesn't even drop out of the 4s, it just automatically assigns to the 3D. But if you want to think about it that way, you could think that it drops out of the 4s to half fill that 3D. So copper and chromium do this, but actually the entire families, all the elements beneath them do the same thing. So copper and chromium will do that, but also will molybdenum and tungsten and silver and gold. Those underneath them in the same columns, which are called groups or families, will behave the same way. And so they'll actually have just a single electron in the S instead of the 2 that you think that they should have. Weird, eh? But the only ones that I'm going to ask you to memorize, even though I'm telling you that they do it for the entire column, are just these 2. These 2 are the ones that you need to know. So in that 4th energy level, you'll lose an electron out of the S and half fill the Ds for chromium and completely fill the Ds for copper. So yeah, it's showing you the same thing here. Okay, so that concludes what we're going to talk about today. Yeah, that concludes what we're going to tell you. You have some homework over the weekend. We've already done the quantum number worksheet. That was the 10 questions we did at the end of the period, well, kind of in the middle of the period yesterday, for which 4 quantum numbers don't necessarily work. Or if they do work, well, if they worked, and if they didn't work, why didn't they work? But you do have some problems to do out of the book. All of them are electron configuration. So that'd be good practice for the weekend. So, all right, guys, sorry I didn't see you today, but I will see you on Monday. Okay.